Right, question 72. Uranus is an average distance 2.9 times 10 to the 12 meters from the Sun. Calculate the solar constant for this planet. Now, in calculating solar constants, you need to consider the source of the energy, which is the Sun, and consider how the energy of the Sun is spreading in all different directions. So whatever power you're getting, that is energy per second, joules per second, okay, that's all getting spread out over a wider and wider and wider surface area. So you can imagine a giant sphere spreading out. Now, at the distance between the Sun and Uranus, which is 2.9 times 10 to the 12, what you've got there is a huge, great big sphere. And so, in order to calculate the intensity, which is joules per second per meter squared, okay, you need to work out how much of this energy that's moving every second is going to fall on 1 square meter at this distance. And for that, you need to use the formula power over the area of a sphere, which is 4 pi r squared. And you do need to learn that off by heart. So if we substitute the values in for this relationship, we'll get as follows. Now, from previous questions, we know that the power of the Sun is equal to 3.8 times 10 to the 26. If this was a proper exam question, you'd be given this information, so you don't have to learn it. And then we substitute our values in for the radius, but don't forget to square it. And you should get an answer of 3.6 watts per meter squared. Now, part B. Now, this is a crazy question. But if you can do this, you can pretty much do everything. Estimate the surface temperature of Uranus, assuming it has values of albedo and emissivity that are the same for the Earth. So let's consider what's being asked here. First of all, you need to try and figure out how much energy is going to hit this planet in the first place. That's a terrible planet. Let's try that again. Now that's much better. So we have a solar constant, which is great up until a point. A solar constant will tell us for every square meter, 1 square meter, how much power is reaching this planet. But I don't want to know that. I want to know how much energy is going to reach the whole of the planet per second. So it's almost as if I have to think, okay, what is all of this energy going to be? And that's quite easy to work out, because all you need to do is multiply your solar constant by this area. Okay, now this area is actually a flat disk. If we were to look at it from this perspective, imagine this was your eye, then what you would see would be a cylinder, right? You'd see a circle of light hitting the planet like that. So in order to work out the total energy hitting the planet, you would just use the area of a circle. Like that. So you have your solar constant, which is the amount of energy per square meter, times the area here, which is a circle. Okay? So let's just work out that calculation. Okay, and here we go. We've got the solar constant times the area of that disk of energy hitting the planet. Okay, so we've got 7.3 times 10 to the 15 watts. Okay, so we've gotten rid of the meter to the -2 now. And now let's consider what we have to do. It's a long story. So what you've got now is a planet which is receiving a lot of energy. So this is your energy in. So the first step is how much energy is actually getting absorbed, because we can forget about the reflected energy. That one just scoots off somewhere else. So the first step will be to work out the absorbed energy, and that's to do with albedo. Okay, and we'll do that calculation in a minute. Now, why do we need to know this absorbed energy? Because we need to work out the surface temperature as it emits. But why is it emitting? What's going on? Well, if something is absorbed, if a black body, a perfect black body, absorbs energy, it then emits energy. So we need to find out how much is absorbed before we can know how much is emitted, and then the associated temperature that goes with that. But it's not a perfect black body, as is usually the case. So not only do we have to consider the albedo when we're thinking about the reflection and the absorption, we also need to think about the emissivity, because this is not a perfect black body. So let's take that in stages. Let's think about this reflected and absorbed. Let's figure out how much energy is actually absorbed in the first place. Well, albedo is the ratio of the reflected, over the incident. So if you know how much is being reflected, you can figure out what's going on with the rest of it, because what's not reflected is absorbed. So if the albedo is 0.3, and that gives you a measure of the ratio of the reflected, then 1 minus the albedo, which would be equal to 1 minus 0.3, would give you the not reflected, which is the absorbed. Okay, so how much energy is actually being absorbed by the planet? It would be 0.7 times the total energy that we worked out over here when we were working out that disk thing. Okay, so 0.7 times 7.3 times 10 to the 15, which is the energy arriving at the planet. And that gives us 5.09 times 10 to the 15 here. Okay, so that is our absorbed energy. And if this was a perfect black body, then that would be the end of the story. But it's not. So we need to look at the following relationship. P equals, which is for a perfect black body, times the emissivity. Now, more or less, the emissivity of the Earth is about 0.6. There are more accurate values, but that will do for now. So let's have a look at the power that's arriving. Times 10 to the 15. Okay, so we then substitute all the other values. Okay, and let's have a look at our values. There's our power. Okay, you've got the Stefan-Boltzmann constant, our emissivity, and then you have to do the surface area of a sphere, and that should give you, in the end, a value of about 65 Kelvin.